Hello, welcome to my virtual classroom. This is lecture 9, joint distribution functions. This is based on section 2.5 of the textbook. And in this section, we're gonna look at probability functions for two or more random variables. And here, the number of random variables that we have is arbitrary. It's an arbitrary number of n. Most of the theory can be set up for the case n equals 2, and it generalizes to any n. So initially, I'll look at the general statements or general definitions, and then I'll specialize to n equals 2, where the notation is simpler. But here, the idea is that we have a collection of random variables, x1 through xn, and I'm going to start with discrete random variables. And I'm going to define this function, the joint probability mass function for this collection of random variables, x1 through xn. And in here, one thing that to keep in mind is that x1 through xn, they could be any random variables, and in particular, in most cases, they're not independent. And later in the lecture, we will see what happens in the independent case, but this is the object that we use. This function, this multivariable function is the function that we use to compute probabilities for a collection of random variables. So, and it's just a straight generalization of the n equals 1 definition for the probability mass function. So joint probability mass function. And this is for the discrete case. And given the discrete case, you may already know the generalization for the continuous case. So for the continuous case, it's convenient to have the joint CDF. And this is common notation that you'll see in probability. If you're looking at more than one random variable at a time, people call this a joint. So any object that we described for one random variable, you just throw the word joint in front of it, and that means that it's more than one random variable. So for the continuous random variables, it's helpful to have the joint cumulative distribution function, which is defined this way, as the probability that x1 is less than or equal to c1, x2 is less than or equal to c2, and xn is less than or equal to cn. And this is called the joint CDF for this random variables. Again, this is just a straightforward generalization of the n equals 1 case for one random variable. And in here, then we have the generalization for the joint PDF for a collection of random variables. In this case, it's going to be the continuous ones. And it's going to be the partial derivative of the CDF. This is the CDF from the previous slide with respect to each of the variables. And for n equals 2, the idea is that this is measuring the relative probability of having your random variables in a box of size C1 to C1 plus delta C1 and Z2 to Z2 plus delta C2. So this is going to essentially compute the infinitesimal probability or the relative probability of finding a point in this square. And here this is going to be arbitrarily small. So, and then we can use integrals to compute probabilities for this collection of random variables. And again, these are straightforward generalizations, and it's nothing groundbreaking. It's just naming. It's notation at this point. So let's start with an example. This is for continuous random variables. This is an example that's always good to keep in mind to test different ideas or conjectures that you have for random variables, for collection of random variables. And here, x, y are going to be two random variables, and these are going to be coordinates of a randomly chosen point on a region A in a plane. So what we're going to have is the plane, and then we're going to have a region, and we're going to be choosing a point at random, and the coordinates of that point are going to be our random variables. So this is, and maybe let's see, to make it more explicit, B and A. So this would mean that our random, in this case, if we choose this point at random, then it's going to be, then that means that xy is going to be equal to AB. And this is our region A. Typically, people like to use the example uniformly at random, meaning that each point is equally likely or relatively equally likely to be chosen. And in that case, the probability of the joint probability density, Fxy, of choosing the point xy, it's going to be 1 over the area of A. And in here, the idea really is that we want each point to be uniformly distributed, each point to be equally likely or relatively equally likely. So you look at the ratio of 2 points, x, y, and there have to be equally likely. So that means if you look at the ratio of the relative probabilities, x1, or this is going to be x2 and y2 for two different points, then the ratio should be equal to 1 because they're both equally likely or relatively equally likely. So this then tells you that the xy, the probability density function is going to be a constant. And similarly, by the fact that f is the total probability has to add up to 1. If we take fxy, the integral over the region xy dx dy, then we would have constant times the area of A. And this has to be equal to 1. So it leads to the constant equaling 1 over the area of A. So this is a typical example of joint probability density for its two coordinates. You're throwing a dart at a dartboard, and the location of where the dart lands is your random variable. That's your experiment. Two particular examples to think about are a rectangle, where A is a rectangle, and where A is a circle. So just as a foreshadowing, in this case, when you pick points at random, x and y, this x and y are going to be independent. And in this case, if you pick a point at random in here, the coordinates x and y are not independent. We can actually see this explicitly, and we'll come to some computations later on. I'm not going to go too much into it, but in here, you can heuristically convince yourself that this is true, because if you know that x, for instance, if x is in here, if you know that x is in the center, that means that y is going to be some uniform random point in this region. But if you know that x is towards the edge, so this is your x, then this limits the possible range of values that y can have. So x has an influence on y, so this is going to make it non-independent. And then you can apply the same theory, the same idea to the rectangle. If you have x here, then y is going to be any point from here to here, uniformly likely. And if you move x here, then it's going to be the same region. X doesn't really affect it. And so in here you can check that, you can not check at this point, but you can kind of see that even in this simple example, we can find cases where x and y are not independent. And this is the general case. So in particular, the general case is you're going to have shapes that it's going to have not independent, and this is going to be a special case where you have rectangles. All right, let's continue. Now that we have a probability mass function for two random variables or more, or the probability density function of two random variables or more, now we want to do the operation of forgetting information. And this is what a marginal is. That's what you call, if you want to forget information, that's what you're going to call the marginal. If you go back to the example where you're throwing darts at a dartboard and then you get some like x and y coordinate, then for some reason you may not really care about the outcome of the y. So here y, you might not care about y, and you might only care about x. So you might be running experiments where you're getting too much information and you just want to focus on some specific information. And this is the process of forgetting information or taking marginals. And in the continuous case, and this is for the continuous, you have this formula. This is the formula of taking the marginal or forgetting information, and this is the discrete case. And this is going to be the PDFs. This is going to be the joint PDF, and this is the PDF. And again, this is the probability mass function, and this is the joint probability mass function. And throughout all this, maybe you have already noticed that I'm using the subscripts of the random variables to keep track of which random variables are related to the PDFs or PMFs, so that to keep it straight. And in particular, this is going to help us keep track of these two different cases of, this is the joint probability density function for two random variables, and this is going to be the joint probability density function for one random variable. And I'm using the letter F for both of them because it's hard to come up with more notation, especially when you start introducing more random variables. So in here, the subscripts are going to help us keep PDFs and PMFs apart. Keep them, it's going to help us for bookkeeping. All right. So let's look at this formula for the discrete case. And in particular, let me see what I'm doing. Yeah. In particular, what this says, what this process that we're doing, so in here, I should probably put this. So this is the process, if you start with a joint PDF, this is the process of how you obtain the PDF. And here, if you start with a joint PMF, this is the process of how you forget information and you just get at the PMF. So in particular, what's happening here is that you're just looking at all the cases. So in here, you want to compute the probability. This is the probability that x is equal to x. And this, what's happening here is that you're computing the joint PMF is the probability that x is equal to x and y is equal to y. And you're summing over all y. So in here, you're essentially breaking up this probability into different cases. So you know that x has to equal to x, and then you look at all the other possible cases of what y could be, and then you sum over all of them. And this is going to be your process of forgetting information, that you're just going to take any contribution from any y. And this is how you're going to obtain your PMF. This is how you forget information. And similarly, for the probability density function in the continuous case, this is the probability, the infinitesimal probability that x is equal to x and that y is equal to y. And then you look at all the possible values of y, and this is breaking up this infinitesimal probability into different cases and adding them up together. And this is how we compute our marginals, how we forget information if we have too much information. So let's look at an example for two random variables and in the discrete case. And sorry, I forgot to mention earlier that here I've moved to the setting where I'm just doing everything for two random variables. All these formulas generalize to 3 and more random variables, and it's a straightforward generalization, and we're just going to focus on the two random variable case for now to just make notation cleaner. Here we have that x, then here in this example we're rolling two dice, two six-sided dice. The first roll, x is going to be the first roll, the outcome of the first roll, and this is going to be a random variable, and then y is going to be the sum of both rolls. So whatever happens in the first roll and you add it up to the second roll. In particular, we have that the possible values of x is going to be 1 through 6, the possible faces of the dice, and y is going to be the sum of two dice, which is 2 to 12. So in here we want to compute the probability density function of x and y. And this, again, is just going to be, so in here, you should pause the video for a second if you want to try to compute this on your own, and you should try, but this is the way that we compute it, essentially. So we have that this is, by definition, that this is x equals to x, and y is equal to y. And this is x is the first roll, and y is the sum of the two. And in here, the thing to notice is that if you know the first roll and the sum of the two rolls, you actually know what the second roll is, because you can take y, the sum of the two, and subtract the first. So that's going to be probability that x is equal to x and y minus x is equal to y minus x. And this is going to be the second roll, and this is going to be first roll. And in this case, once we have broken it up into this two, reinterpreted the events this way, we know that the first roll and the second roll are independent, and we know that the probability of each of that the probability is independent, and so we can just compute probability that x is equal to x and y minus x is going to be y minus x. It's going to be the product, probability of x. Sorry, I meant to write the product here. Since this random variables are independent, I can write it as the product, probability that y minus x is equal to y minus x. And if it's non-zero, you know that it's going to be 1 over 36, and otherwise it's going to be 0. So in here, this is going to be x is between 1 and 6, and y is between 2 and 12. In fact, maybe let's make it more. I should be careful, because if x is equal to 1, it's impossible for y to be equal to 12. They both need to be 6, so I should say if x is between 1 and 6 and y minus x is between 1 and 6. then it's going to be 1 over 36, and then otherwise it's going to be 0. So this is going to be our probability, then joint probability density function. And again, this is notation, and maybe this might be a little bit too subtle, but you have to be careful with this notation. When I write this type of probabilities, this is the probability that this event happens and this event happens. So I denote it by writing this event, and then I do a comma, and I write this. So for the probability density functions and probability mass functions, I'm writing the probability that multiple events are happening. That's the probabilities that we're computing. So let's continue, and now we have this this joint probability mass function, and from this joint probability density function, we should be able to using the marginal procedure from the previous slide, we should be able to compute, to forget about the information of x and compute the probability that the sum is equal to 3. So this really is just the probability that y is equal to 3. And in here, the procedure of taking the marginal is really considering all the possible cases. So in here, I'm taking taking the marginal of the PMF is going to be, I'm going to just do it by hand without the formula. And essentially, you can always do it like this for each case by case. So if y is equal to 3, then we know that x could be 1 and y is equal to 3. Or x is equal to 2 and y is equal to 3. And since the second row is 1 or greater, then these are actually all our possible cases where for x. And in here we know we can compute the right-hand side using the joint probability mass function, xy. This is going to be 1, 3 plus probability xy, 2, 3. And each of this is 1 over 36 plus 1 over 36. And this probability is going to be 1 over 18. So here, this is the idea behind the marginals. So if you don't care about the second or one of the random variables, and you have the probability mass function, the joint probability mass function, then you just look at all the cases. You fix the random variable that you're interested in, and you sum over all the other possible cases. And this is going to be the procedure of taking the marginal or for getting information. You just look at all possible cases and you sum them up. And these are all the possible cases that you can get y equals to 3. All right, so moving right along. Before wrapping up this lecture, we have 2 major claims for joint probability mass functions and joint probability density functions. The first is that now if we are in the independent case, we have the following claim that the joint probability mass function for the discrete case is the probability mass function so the joint one is going to be the product of the marginals. And this is true for both the continuous and the discrete case. So this is the joint, and it's going to be the product of the marginals, and this is going to be the joint, and this is the product of the marginals. So let's prove this, and let's go through the proof in each case. So in here, the idea is that we're just going to chase definitions. So in here, the joint probability mass function is equal to the probability that x is equal to x and y is equal to y. And now, and since they're independent, we can actually write it as the product. This is the independent condition, probability of y. We use the independent condition there. And now let's write the probability density function for x, and we do this using the marginal procedure. So this is gonna sum over all y, and this is the x, y, x, y. I use the joint probability mass function, and then I rewrite the joint probability mass function as the probability that x is equal to x and y is equal to y. And now I can use independence to write the product of x is equal to x and probability that y is equal to y. And then since I'm just summing over y, I can factor out probability that x is equal to x. And then I have the summation y over c, and this is the probability of y is equal to y. We're almost done here, and I pause for a second so that you can think of this last step for this computation. Then in here, you should note that this summation is going to be equal to 1, because the total probability is going to add up to 1 always. So this, at the end of the day, we have that this is going to be probability that x is equal to x. And similarly, we have that going through the same procedure, the marginal of y is equal to y is equal to probability that y is equal to y. So now, putting all the pieces together, we have this is equal to this is equal to this, and this is equal to this. We obtain the result, the probability x, y, x, y. Probability that x times the probability mass function y, y. And this is what we wanted to prove. In this proof, I actually just needed the independence condition right here. In here, I technically don't need the independence condition. And even for dependent random variables, the marginal is always equal to probability that x equals to x. I chose to use the dependence here to make it more explicit, to see that this probability adds up to 1. Alternatively, you can do an argument to show an alternate argument to show that this is equal to this and this is equal to this. So these equalities are also true for non-independent random variables. So this is going to be our proof for the discrete case. Now let's do the proof for the continuous case. And here we'll see what we have here. We have that the definition of this is that dx dy, that the joint PDF is the partial derivative xy of the CDF. And in here, we have that the CDF is the probability that x is less than or equal to x and y is less than or equal to y. And now we use our independence property, and we have dx dy d squared, and we can write the probability as the product of two probabilities, y is less than y. So now, once we've write it as a product, we can distribute the partial derivatives separately. So we can have the dx probability that x is less than x, and dy, probability that y is less than y. And now this corresponds to the probability density function for x and the probability density function of y. And this is our proof. And it's essentially the same proof as in the discrete case. And the main idea is to write this as a product of the two probabilities, and then once you separate into a product, then it becomes the probability density function for each of them. Okay. So in here, again, let's go over the statement is that if x and y are independent random variables, then their probability mass functions and the probability density functions are just the product of the marginals. So the joint is the product of the marginals. So let's go back to our example of two rolls of a die, where x is the first roll and y is the sum of two rolls. Are x and y independent? So in here, this is something that we can do explicitly. If x and y were independent, probability of x, y, let's say 1 and 3, should equal to the probability x is equal to 1 times probability that y is equal to 3. So in here, we've already computed that this is equal to 1 over 36. And we've also computed that the probability that x is equal to 1, this is just the first roll, it's going to be 1 over 6. And in the previous example, we computed that the probability that y is equal to 3 is going to be 1 over 18. So we have that this is 6 times 18. It's not going to be 1 over 36. I don't know what that is off the top of my head, but this is too small. Because, let's see. Let's write 6. I know that this is, if I distribute a 2, I have 1/3 times 1 over 36. So it's not 1 over 36. So here we have that these are not equal to each other. So this is one specific way that you can prove that two random variables are not independent. You can just like, that two random variables are dependent. Or not independent, I think it was right. So you can just pick specific values where this identity doesn't hold. Then if you say that C, if you call C to be the second roll, minus X, second roll, you can see that the probability, the joint probability, you can compute this of PX Z, X, Y, it's going to be 1 over 36. And then you're going to have that PX of X is going to be 1 over 6 in the non-zero cases, and PZ of Z is going to be 1 over 36, 1 over 6 in the non-zero cases. Then you're going to have that 136 is equal to 1, 6 times 1, 6. So in here, for two independent random variables, we can check that the joint probability mass function is indeed equal to the product of the marginals. Sorry, I meant to do this. C. Okay. So for independent random variables, the key takeaway is that the joint density functions is the product of the marginals. Now, let's go to the last claim for this lecture. And this is that the expected value is linear for any two random variables. So again, we just did the independent case, but this is actually true for any random variables, x and y. X and y could be dependent, and what we have here is that you can take out summations outside of expected value. So the expected value of the sum is going to be the sum of the expected values. This is the claim. And this is very helpful for computations because in here, to compute this quantity, you need a joint probability density. So to compute this side, you need a joint PDF. And to compute this side, you just need marginals. So you just need the PDF. This is a two-variable function. And this is, each one of them is a one-variable function. And one-variable function. And this is a 2D integral. And this is a 1D integral. 1D integral, each one. So in here, this is the main advantage of this identity, that if this you have two random variables, then technically you need a joint PDF to compute that, to compute this expected value. But in here, it turns out that it's sufficient to just have the marginal PDFs or one-dimensional integral. So this computation often tends to be simpler. And this is why we like this identity, this linearity. We'd like to take the summation outside of the expected value to simplify our computations. So in here, the key observation is obtaining the distribution for x plus y. So I'm going to call it C, and through the proof I'll call it Z, the sum of x plus y. Then in here, I want to obtain the probability density function for Z. And here I'm doing it for the discrete case. So what this means is that it's the probability that x plus y is equal to C. And for this, I need to consider all the possible cases where x plus y is equal to C. So if I let the first random variable be equal to x, then for x plus y to be equal to C, then y needs to be Z minus x. So if x is equal to x, then y needs to be Z minus x. And then I need to consider all the possible cases, which is the summation over all x's and z. And then here, this probability is equal to the joint probability mass function. And I have that the probability distribution of probability mass function of z, the sum of x and y, is equal to this sum. This is called a discrete convolution. Convolution is an operation that you'll see often in different mathematical settings. So here is one specific interpretation of what a convolution is. It's just the operation for taking the joint or the probability mass function of the sum of two random variables. In the continuous case, we have a similar computation where you can find the probability density function C by taking all the possible values where x is equal to x and y is equal to C minus x, and summing over all the possible cases. So this is just a generalization to a continuous case, and this is going to be a continuous convolution. So this is the key observation. This is the key thing that we need to compute to prove our lemma. So in here, let me give you the proof for the continuous case. So this is going to be using the notation from the previous slide. This is the expected value of C, where we have that this is the integral over all the reals, where we have C times the probability density function of Z, dZ. And this is just by definition. And this is notation to make the computations here seem more natural. And now by the observation in the previous slide, we have that the probability mass function is going to be an integral over R. So I'm taking this formula. So I take f x y, and then x, and then z minus x dx dc. So this is going to be R2, then this is z, and this is fx y x z minus x dx dc. And now we're gonna do now we need a u substitution. We have that we write y is equal to c minus x, and then this is gonna tell us that this is a double integral, R2, x plus y, f x y, xy, dx, dy. No, dx, dy, yeah. And then we decompose the integral R2, x, fx, y, xy, dx, dy, plus R2, y, f, x, y, xy, dx, dy. And we're almost there. And here you should notice the marginals. And here we have two-dimensional integrals, and we're going to take one of them to create a marginal. So in here, what we do, for the first integral, we integrate over y, all the possible values of y. And we obtain that this is fx, x, fx, x, dx, r. And for the second one, we integrate over all x to obtain a marginal, the marginal density function. So this is y, fy, y, dy. And now we can recognize this formula as to be the expected values of x and y respectively. So we obtain expected value of x and expected value of y. And this established what we wanted to prove, that the expected value of x plus y is equal to the expected value of x plus the expected value of y. The proof for the discrete case works similarly. You just need to kind of do everything in summations instead of integrals, but the idea is the same. And that wraps up the lecture. Thanks for tuning in. Goodbye.